My name is Shawn Coyle, and I'm here today to talk about recirculating aquaculture systems. Aquaculture is the farming of plants and animals in water. This can be either in freshwater or in marine systems. There are basically three different types of aquaculture systems. There's open systems, which are typically net pens and cages. Often this is ocean ranching. There's semi-closed systems, which are ponds and raceways. And then there's closed recirculating systems or biofloc systems that are generally indoor or tank culture systems. Open systems are when organisms are reared in natural systems where there's no diversion or pumping of water. This typically happens in ocean type environments. Often oysters and bivalves, mussels are cultured in either rafts or in longline systems, and salmon are cultured in net pens throughout several different areas throughout the world, and often in fjords or in protected areas in ocean environments. Semi-closed systems or aquaculture systems, which are man-made impoundments where water is diverted from natural flows or is pumped. And these include ponds and raceways or flow-through type systems. Closed systems are where the water is reused and there's little or no effluent, and the water's filtered and treated and reused. Water systems can be broken up into either flow-through systems, where there's a one-time use of water, or recirculating systems where the water is reused. This diagram just depicts a flow-through system where the water source can be pre-treated, either through screening. Then the water runs through the rearing tank and is discharged as effluent. So basically you have the same amount of effluent as you do incoming water. The advantages of flow-through aquaculture systems are their simplicity, their lower cost, and they require less skill to operate. The disadvantages are that you have very little environmental control, and contaminants and pollutants can easily enter your system, and you have greater regulatory constraints because the water is being discharged back into natural systems. Recirculating aquaculture systems, we still have a water source that is used to fill the rearing tank, but once the rearing tank is filled, the water is recirculated between the biofiltration and the disinfection systems, and there's very little effluent that exits the system. The advantage of recirculating aquaculture systems is that we have greater environmental control. The water is generally free of outside contaminants as it's treated as it comes in and is reused, and there's fewer regulatory constraints. The disadvantages are higher cost of initial infrastructure development, higher skill level and complexity of the system, and the buildup of toxins and pathogens. The definition of recirculating systems they are systems in which the aquatic organisms are cultured in water, which is reconditioned and reused. So why recirculate? Recirculating systems conserve water. They permit higher density culture in locations where space and water are limiting, such as maybe in a metropolitan area close to a relatively large city. They minimize the volume of the effluent. They allow for increased control over the culture environment, improved biosecurity, and greater environmental sustainability than other types of systems. There's also lower water demand in recirculating systems. It's just an example of how much water is generally required to produce a 1-pound fish. It's about 12,000 gallons in a raceway or a flow-through system. It's 1,200 gallons in a pond, and only 12 gallons in a recycle system. This gives you an idea of the daily water reuse rates. So in an open or flow-through system, there's no reuse. The water just bypasses through the system and out into the natural environment. In a semi-closed system, such as a pond, it can be around 50% reuse, where the water is basically static. But then when we harvest the fish, we have to drain all the water out of the system, and then it needs to be replaced. Closed systems can attain upwards of 100% of daily water reuse. Characteristics of the culture tank effluent from a recirculating system. There's a high concentration of suspended and dissolved solids. There's a high amount of ammonia, high concentrations of CO2, and low levels of dissolved oxygen are typically characteristics of culture of recirculating system effluent. Water quality monitoring is very important in recirculating systems. We often check ammonia, alkalinity, pH, and dissolved oxygen. It's very important to monitor these parameters. Ammonia is the toxic byproduct of protein digestion. Fish excrete ammonia passively through the gills, and the majority of the ammonia is excreted through the gills. This is a very efficient system. However, if the ammonia in the culture tank attains a very high rate, then the ammonia can also diffuse back into the fish from the culture water. Removal pathways for ammonia. There's basically 3 different pathways where ammonia can be removed from water. Photoautotrophic removal by algae, autotrophic conversion to nitrite, then to nitrate by bacteria, and heterotrophic bacterial conversion to microbial biomass. Heterotrophic bacteria utilize organic carbon and ammonia for growth. One example of this type of system is the activated sludge wastewater treatment system. And in this system, water is kept movement to keep the bioflux suspended, and it's very important to aerate and oxygenate the water. Nitrification utilizing autotrophic bacteria is generally performed in a biofilter where ammonia is oxidized to nitrite and then to nitrate by 2 different types of bacteria or genera of bacteria. Nitrosomonas bacteria break down ammonia to nitrite, and Nitrobacter bacteria break down nitrite to nitrate. Both use inorganic carbon for growth. Autotrophic bacteria use inorganic carbon, and when I say that I mean CO2, carbonates, and bicarbonates for growth, and this reduces the alkalinity of the water. The alkalinity should be maintained at around 100 milligrams per liter by the addition of baking soda. pH is another indicator of alkalinity, where this nitrification process lowers the pH as the alkalinity is consumed, and is also an oxygen consuming process. You can see as the ammonia is converted to nitrite, it produces 2 hydrogen ions. As the hydrogen ions increase in the water, this makes the water more acidic. Fish also respire CO2, which also lowers the pH. Adding buffers such as baking soda ties up the excess hydrogen ions and buffers the water. One rule of thumb is to add 10 to 20% by weight of the amount of feed that you put in the system of baking soda to maintain the alkalinity around 100 milligrams per liter. This slide depicts the biofilter break-in process. As you can see, the ammonia starts out high, and that's where we would add ammonia to the system. And as the bacteria start to colonize the biofilter, you can see a drop in the total ammonia. And then later you see an increase in nitrite. So the Nitrosomonas first colonize the biofilter, and then the Nitrobacters start to colonize when you see a drop in nitrite and an increase in nitrate. This process generally takes about 4 weeks. Applications for recirculating systems are many. Broodstock maturation, larval rearing systems, nursery systems, and research systems. They're also used for short-term holding of fish and ornamental and display tanks, such as aquaria. They also can be used for high-density grout of food fish, but they're very different in their approach. Classification of culture systems by trophic level. Trophic level basically distinguishes the level of nutrient load. These terms are typically used to describe natural lakes, and they describe how much nutrient load or nutrient density is in these different bodies of water. So I'm going to use them to describe the different types of recirculating systems that are used in commercial aquaculture. Oligotrophic systems are characterized having excellent water quality. The water is very clear, such as in display aquaria, and they're most frequently used for breeding purposes and with very sensitive and high value species. I'm going to just show you a few pictures of oligotrophic systems. Very clear water. These are larval fish. This is a feed training system, and you can see how clear the water is. This is a research system. This is a salmonid grow-out system in cold water. Salmonids, or trout and salmon, require very clear and clean, pristine water. And this is a retail display tank where these fish are being sold to market. Mesotrophic systems are kind of in the middle, and this describes the bulk of high-density production system where risk and economics must be carefully balanced to achieve profitability. You expect some deterioration in the aesthetics. The water's not going to be crystal clear. We maintain the water quality at safe levels, however, not perfect. The oxygen will typically be greater than 5 milligrams per liter. The toxic metabolites, as in total ammonia, nitrogen, and nitrite, should be less than 1 milligram per liter, and the total suspended solids is generally less than 15 milligrams per liter in a mesotrophic system. This is also a salmonid system for trout grow-out. A tilapia system, you can see the water, although it looks clear, you can see that it's a little bit brown. It's kind of a tannic color. Another tilapia system. This is a large outdoor system for hybrid striped bass. And here's an aquaponic system with tilapia. Eutrophic systems exist for the grow out of the most tolerant species that show vigorous growth under moderately deteriorated water quality conditions, so pretty tough fish. Dissolved oxygen levels are maintained at the economic optimal level, which can be as low as 3 milligrams per liter. Ammonia and nitrite are typically less than 2 milligrams per liter, but greater than 1. Water quality is marginal for species that are not very tolerant, but is acceptable for the most tolerant species. Species that live under similar conditions in their natural conditions are used, tilapia being one. Total suspended solids are generally greater than 15 milligrams per liter. Here's an example of a eutrophic system. You can see the brown water. This is actually a converted hog barn that was used for tilapia production. Another example, tilapia. This is an indoor mixed biofloc system. This is a marine shrimp that were raised in these biofloc systems, which are also considered eutrophic systems. Another example of biofloc, and this is actually biofloc research, but you can see the brown water. In commercial recirculating systems, typically 90 to 90% of the water is recycled or reused daily. So 1 to 10% is replaced daily. The main filter components are the clarifier and the biofilter. The clarifier removes settleable solid waste, and the biofilter removes dissolved toxic waste. An integrated treatment is basically an assembly of components that creates an artificial environment that's suitable for the production, breeding, or display of aquatic animals. The system must be reliable, cost-effective, and it must be compatible with the intended use. The system design is based on your production needs or expectations, economics, and also market. I'm going to talk about system components now. Solids capture and solids removal, both settleable solids and fine dissolved solids, are critical to waste management. This gives you an example of different components based on the clarity of the water, based on whether or not we're going to manage our system as an oligotrophic system all the way to eutrophic. And it's based on particle size removal. So just a coarse screen or a relatively crude rudimentary filters will remove particle sizes down to 100 microns. As we get into tube settlers and granular media filters, we can remove smaller solids down to maybe 30 microns. But to remove the very smallest, we use diatomaceous earth or foam fractionation to remove the very fine dissolved solids that are down to below 10 microns in size. So now I'm going to talk about solids removal, and we'll start with the most simple methods of solids removal. The settling basin is probably the simplest. And using a settling basin, you try to keep the solids intact, and you need retention times of 15 to 60 minutes within the settling basin to allow the solids to settle. It may only remove less than 10% of the solids, and typically only the largest of the solids are removed using a settling basin. A tube settler, in which the water comes in and then has to go through media before it outflows back to the tank, are better at removing sludge from the system. This is a very crude method where we're using just filter fabric to remove solids from the culture water. Bag filters are also used. Floating bead filters have become real popular, and they offer both solids removal and nitrification within the same system. This slide shows you the operation of a bead filter. Under normal operation, you can see where the water flows up through the bead filter and then exit back to the tank. And the media is suspended in the top of the tank. It's floating bead media. When backwashing, in this particular system, it uses a motor and a propeller which churn the beads. So you would turn the pump off and you would turn on your propeller on the top and churn the beads, which would break up the solid waste that's been trapped. And then you would turn off the propeller and allow the solids to settle to the bottom, and then you would discharge the solids out the bottom of the filter. Rotary drum screen filters are probably the most high-tech solids removal system, and they're used generally in very large systems, and they're quite expensive. In this case, the water flows out of the culture tank and through the screen, and then the screen actually has a water spray that blows the solids off of the screen and where they're discharged out into the effluent. Diatomaceous earth and sand filters remove very fine particles. They're very efficient at maintaining very clear water. However, if the water is dirty, they'll clog up very quickly. So they're really only used in the cleanest water systems for polishing. Foam fractionators remove fine and dissolved solids and foam from the water surface, and are very good at removing dissolved solids, not settleable solids. So pumping water, there are several different types of pumps. Generally, you would have to pump the water through the recirculating system. You can use submersible pumps or inline pumps. And this is an example of an airlift pump in a raceway where the air is injected, and I'll have another example of an airlift pump that you can see better, but it's a very efficient way of moving water. This is also an airlift pump, and you can see that the air is injected at the bottom into this tube, which the water level would typically be at the same level as inside the tank, but as the air escapes out through the PVC pipe, it lifts the water, thus airlift. Oxygen is the first limiting factor. We need to supply oxygen to recirculating systems. It's very crucial in the event of a power failure. You basically would have, if your loading density or your biomass density in the tank was 1/4 pound per gallon, it would take about 16 minutes for your dissolved oxygen to drop to below 3 milligrams per liter, which is considered crucial for some species. In the same system, if you had fish biomass density of 1 pound per gallon, you drop below 3 in less than 6 minutes. So you can see that how crucial it is to have backup systems. And those backup systems can either be power generators for power failure, or also oxygenation systems to back up your aeration. Okay, so what's aeration? What is oxygenation? What does that mean? Aeration is using atmospheric oxygen, just normal air, to add oxygen to the system water. However, atmospheric oxygen only contains about 21% oxygen. So that's what you're adding to the water. Where oxygenation uses pure oxygen, so you're adding 100% oxygen. This is an example of an aeration system using a blower and also medium pore diffusers. So blowers are designed for high volumes and low pressure and are generally the most cost-effective method of aeration. Oxygenation, where you're adding pure oxygen to the water. There are several different ways to do that. Typically, liquid oxygen is used, or oxygen generators are then supplied through very fine pore diffusers, really small bubbles. Now we're going to talk about different biofiltration systems. All biofiltration systems use biofiltered media. They basically provide a lot of surface area for the nitrifying bacteria, Nitrosomonas and Nitrobacter, to grow on. Here are some different examples, different types. Mixed bed or moving bed reactors have become real popular using coldness media or macaroni-shaped media. They have a very high nitrification rate, and they also are self-cleaning, so the old bacteria colonies kind of tumble off as they churn. But there's no solids filtration in these type systems. This is a moving bed filter. You can see the media, coldness media. Another example, the same type of system. You can see where the media is churning through aeration. You can see where it's not real clean white. This media is colonized by the bacteria. That's a good color. Disinfection. Some systems require disinfection of the water, particularly when water clarity is important. UV technology, or ultraviolet light, is quite popular. You use a very narrow spectrum of light that is germicidal, basically. Around 264 nanometers, I believe, is the best spectrum, and as long as the water is relatively clear, the light passes through the water and kills bacteria that are loose in the water. Ozone is another method. And if you need other assistance, this is a great book by Dr. Timmons and Dr. Ebling. Covers a lot of good information here on recirculating systems.